the indefinite integral, general solutions, and particular solutions. When we write an integral that has a lower and upper limit, and we are asked to evaluate this integral, we were using the fundamental theorem of calculus, part 2, which says find the antiderivative of the given function in the integral, evaluate it at the upper bound, and evaluate it at the lower bound, and find their difference. So this is our definite integral, and this is, again, FTC part 2. But what if we faced with an integral that does not have a lower or upper bound, and we were asked to evaluate that? Actually, less steps are required. To evaluate what is called an indefinite integral, so when we don't have a lower and upper limit, we just find the antiderivative, and then we have to tack on this plus c. And the reason being is because when we're finding an antiderivative, remember that this function should be some function that when I take the derivative of that, I get the function that's inside this integral. And therefore, because of that, my antiderivative could, in theory, have some additional constant tacked on at the end, because we know the derivative of a constant is 0. So to consider that possibility, every time we evaluate an indefinite integral, we tack on this plus c to our antiderivative, and this is called the constant of integration. Because we must take into account the possibility that our antiderivative may have had a constant on the end, and we know, again, taking the derivative of a constant is 0. So that is the difference between the two scenarios. So if you're asked to evaluate a definite integral, FTC part 2. If you're asked to evaluate an indefinite integral, it's antiderivative plus c. Now, where does this come into play with the indefinite integral? One of the common cases is what we call general solutions and particular solutions. So first, we'll talk about what the general solution is and how that relates to the particular solution and what types of problems you would be working with where that comes into play. So here's an example. We have a derivative of some function y that equals cosine x plus sine x. And we also know that when we evaluate that function y at pi, we get 1. It may ask you to solve this, what's called a differential equation. This is a differential equation because it has a derivative in it. So it's an equation with a derivative, hence the name differential equation. Now this is a first derivative. So how do we solve this? Let's say we're trying to find the function y, whose derivative is this. That sounds awfully like finding antiderivatives. So in order to solve this problem, we can integrate both sides. And if we integrate both sides, we know the integral of dy dx, the antiderivative of dy dx should be y. The antiderivative of the right side, so imagine we have a dx here, but in general I just threw on the integrals to illustrate the point, but the antiderivative of cosine is sine x, the antiderivative of sine is negative cosine, and then because we're evaluating an indefinite integral, because all we're trying to do is find the antiderivative, don't forget that there's a plus c here. Now the plus c indicates that this answer that we got is a general solution, meaning the solutions that we have to this differential equation are all going to come in this form. The antiderivative of sine x minus cosine x, we add on the constant of integration to account for the possibility that there is a constant exists. And then what changes one solution from another is all based on this initial condition or initial value that we are given. That initial value is going to allow us to find out what the constant c should be when we have that initial condition. We know that this equation equals 1 when our function is evaluated at pi. So we have 1 equals 0 minus a negative 1 plus c. So we have 1 plus c, so solve for c, so c equals 0. As soon as we find the value of c, our solution to this problem with this initial condition, we can plug in that value for c. This is the particular solution. It's particular because this is the solution we get, again, when we implement that initial value or initial condition. So that's the difference. The general solutions, there's an infinite amount of general solutions to that differential equation. As soon as we incorporate or introduce an initial condition, we can now find the value of C. And upon finding the value of C, we found a solution that is particular to that case. Some additional examples. Here's a differential equation with a first derivative. We want to find the function y, whose derivative is given and meets that initial condition. So integrate both sides. The antiderivative dy dt is y. The antiderivative of 2e to the negative t with respect to t. We'll notice that there's a composition here. So composition, let's reverse that chain rule application. So we're going to do the derivative, the antiderivative of the outer. So the antiderivative of e is e, still composed with the inner, but instead of multiplying like we do when we differentiate, we're going to divide by the derivative of what's inside. So we're going to have a -1 out front. So let's just make this more compact and write this. Plus c, here's our general solution. Now we know our antiderivative is correct. If we take the derivative, then we get what's inside, or what the problem started with, because we have a derivative given. Now, general solution, how do we find the particular? We know it equals 0 when we evaluate at natural log of 2. This will allow us to find the value of c. So how can we simplify this? Our log rules, we can move that -1 back to an exponent position. 2 to the -1 is the same thing as 1/2. And e raised to a natural log of some number is just whatever that number you're taking the natural log of is. So we get -2 times 1/2 plus c. -2 times 1/2 is -1, so c must equal 1. So now we know the particular solution to this differential equation is -2e to the -t plus 1. And then one more example. Let's say we're given a differential equation with a second derivative, and we have an initial condition for the first derivative and for the original function y. So we still want to integrate both sides. Upon integrating both sides, the antiderivative of that second derivative is the first derivative. Which is going to be negative cosine of theta plus c. We know that when we plug in 0, we get 0. So cosine of 0 is 1, so c is equal to 1. So the particular solution after doing the first derivative is therefore negative cosine of theta plus 1. Now we have to find the original function y, so integrate both sides. Negative sine theta plus c. Don't forget that plus c. We know when we plug in 0, we get -3. Sine of 0 is 0, so c must equal -3. So let's finish this thing off. Y should equal negative sine theta plus theta minus 3 to double check our work. If we plug in 0, do we get -3? Yes. If I take the derivative, do I get what I think the first derivative should be? Negative cosine plus 1? Yes, I do. Then when I check my first derivative, if I plug in 0, do I get 0? The answer is yes, because cosine of 0 is 1, so -1 plus 1 is 0. When I take the derivative of that, do I get sine? And the derivative of cosine is negative sine, so the derivative of negative cosine is in fact positive sine, so everything checks out. Here is the original function. Now, what I'm doing by integrating both sides, that isn't technically what we want to format, and you'll see down the road, this is kind of just like an informal approach to what we're doing, because you'll see further down the road when we have the differential equations, we're going to be separating variables. But I just wanted to give you an idea of how we can approach these problems, where general solutions come into play and where particular solutions come into play. But the idea of your anti-differentiating both sides does hold, that is valid. But you'll see some of the differential equations can get a little more tricky We're going to have to do a little more work so that integrating both sides, notation I'm using is rather informal. But the main goal of the video was to introduce the indefinite integral, which is just evaluation is going to be antiderivative plus c. The difference between that and the definite integral, which is antiderivative evaluated at lower upper and finding the difference. So make sure you can recognize the difference between those two things and what to do when. Then again, introducing what is a general solution and then what is a particular solution and how to find those C constants for the particular solution when you're given an initial condition. So that will conclude this video.